A while back, I started a project to build basically a compass as a tool to assist astronomy viewing. I've been working on it fairly steadily, and although the project isn't complete, I'm pretty far along now. About halfway, in fact. It's enough to see how well some design decisions worked out, or not. A normal compass shows directions on the surface of the Earth. So does my astronomer's compass. But it adds skyward directions. I designed it to help locate astronomical objects. I want to know which direction to look in or which direction I am looking, including up. There are smartphone apps that do that, but I want to build a device of my own. My astro compass is intended to augment visual observations made with a binocular or maybe just naked eye viewing. So what I've been doing in the past several months, the most visible progress is the Enclosure. The Enclosure is a remix of the Ultimate Box found on Thingiverse. I put in an extra hole to attach the compass to a tripod, plus a hole for a push button, and a pair of small holes to mount a red dot finder. The holes that take bolts use threaded brass inserts. The compass controls need to be easy to access. Sometimes I'll be holding the compass and binoculars together in my hands, and I don't want to let go or lose my grip when I adjust something. That's especially an issue with the push button. That's why it's separate from the encoder and mounted on the top of the Enclosure. I can more easily reach it there with the finger than to try to press the encoder knob with my finger or my thumb. And if it serves two functions, the knob is prone to turn a little when I press it. The front panel has reinforced holes for the OLED display and the encoder. The rear panel accommodates the on-off switch and supports the battery holder. I couldn't manage changes to the original panels, so these aren't from the original Thingiverse box. I used FreeCAD to make the panels. And of course, all the electronics have to fit inside the Enclosure. I 3D printed individual rafts, one for each sensor breakout board, so I could try various arrangements. I found several simple arrangements where the components comfortably fit together. The final arrangement will affect the overall size of the Enclosure. To mount the individual breakout boards, the small individual rafts are merged into a composite platform to mount inside the Enclosure. Those hollow tubes will take threaded brass inserts. The boards connect to each other by wire harnesses. I've changed my mind about some components discussed in the original design video from long ago. For instance, I've traded out the MPU 6050 Inertial Measurement Unit, or IMU, for a BNO055, a different kind of IMU. The 055 has a magnetometer built in, which the 6050 doesn't have. I also like the idea of self-calibration. To calibrate the 055, all I'm supposed to do, basically, is wave it around. Actually, there are several calibration methods. They have a lot in common, but there are variations. I'm about to exercise a hybrid procedure taken from several methods I've seen on YouTube. Calibration begins by rolling and pitching the device, pausing briefly as each axis of the device becomes roughly vertical. In other words, each of the 6 sides of the box gets a turn at being face up. This part of the calibration affects the accelerometer. It more or less is discovering gravity. Then we yaw, or pan, the device, pausing at or near cardinal compass points, north, east, south, and west. Then swing the device around in a figure 8. This affects the magnetometer. Now it should have a good idea where north is. Finally, placing the device on a stable horizontal position for a few seconds calibrates the gyroscope and finishes the calibration process. In addition to the 3 internal sensors, the gyroscope, accelerometer, and magnetometer, there's a 4th, pseudo-sensor, called system. It's been described as an aggregate calibration of the other 3. When it says it's calibrated, then the entire system presumably is calibrated. But I'm not convinced, though, because the system calibration seems to come and go, with or without the other 3 necessarily showing that they're calibrated. Once through this ritual, calibration isn't always complete, and more often than not, the fusion results aren't very accurate. A second run-through, and sometimes a third, seems to improve the accuracy. Reluctantly, I changed out the I2C Encoder Mini. It's a clever device, but I decided to use a simple encoder filtered through an LS18, a 3-channel debouncer IC. The push-button switch is connected through the debouncer as well. The LS18 eliminates the need for discrete debounced components and pull-up resistors. Like I said, the project isn't complete, but I did create a manual mode where I could use the encoder to substitute for any of the sensors. I set up manual mode so that I could check out the math pipeline converting raw data to celestial coordinates before I'd written the software to support the actual sensors. In manual mode, I don't need to calibrate either. In a manner of speaking, this makes the compass also function as a celestial calculator. My GPS driver isn't written yet, and without it, the compass can't get its location or the time. But in manual mode, I can set those. Once I have the GPS driver, the compass will get those values automatically, but I'll still be able to override them to set the location somewhere other than where GPS says I am, or set a time other than the time it says. For instance, 6 hours from now, tonight at 9 p.m., my compass says that the local sidereal time will be 2014, and the U.S. Naval Observatory agrees. Let me introduce Stellarium, a free open-source planetarium. Since I haven't yet been able to properly calibrate the BNO-055, I'll substitute Stellarium to look up the azimuth and altitude for Altair and enter the coordinates manually. Tonight at 9, 2014 local sidereal time, Stellarium says Altair will be located at 190 degrees, 5 minutes azimuth, and 57 degrees, 3 minutes altitude. I'll set that azimuth and altitude that I just read from Stellarium and see how close my compass comes to Altair's celestial coordinates. (190.05) and 57 degrees, 3 minutes. Stellarium reports that Altair's celestial coordinates are 19 hours 51 minutes right ascension and 8 degrees 55 minutes declination, so 1951 and 855. Not bad for an 8-bit microcontroller. I bypassed the BNO-055. You saw me on camera manually setting Altair's azimuth and altitude. It proves the math works, but I need to refine the BNO calibration so I can use that sensor. The BNO is within a few degrees, but I need to learn more about its calibration to improve its precision. I'd like to be within 2 degrees, and I mustn't forget to compensate for magnetic declination, too. That pretty much concludes this State of the Project update. As more milestones are reached, I'll post more updates, hopefully more frequently. Thanks for watching.